Hey all, so we are going to introduce our third and final method of different kinds of proofs for this section. So we're jumping into chapter 6 here. So this will go along with direct proof, contrapositive proof, and now we're going to talk about contradiction. And that's what we're doing for the next 2 weeks before going into winter break. And that's going to sum up this section of the book. So get yourself ready for notes, and we are going to do a couple problems here with contradiction in this lesson, and we'll do a couple more tomorrow. So the idea of contradiction is that the first thing that you're always going to do when you start a contradiction proof is you're going to start by assuming that the statement you want to prove is not true. So number one, assume that the statement is false. And so then, for example, in this case, if I'm looking at number one here, prove that root 2 is irrational, the first thing that I'm going to do here is I'm going to say that root 2 is not irrational or is rational. So similar to the contrapositive in that you're negating the statement. So assume that it's not true. Now, the next thing that you want to do is we're just going to find the logical fallacy, or you can even think about this as an inconsistency. And once we find that, inconsistency, there's a reason I'm not a spelling teacher. Once you find that, then you're like, okay, I've made a mistake somewhere along. And this inconsistency could be dividing by 0. It could end up being a distance is negative. It might end up being that two numbers are equal to each other, even though we said specifically that they weren't. So all of these are the sort of things you're looking for. So in this case, we are going to say, all right, well, say root 2 is rational. So we're going to work from that assumption. So if it's in the rational set, remember, that's Q with that line. Then what that means is that root 2 is equal to P over Q. It's a rational number. It's a fraction where P and Q are in the integers. And this is what's called, they are relatively prime. Relatively prime, which means that they share no common factor except for 1. So what this basically means is that it is a simplified fraction. So root 2 equals 7 over 10. Those are relatively prime. That's a simplified fraction, unlike 14 over 20. Now, every rational number has a simplified version. We're just going to say, okay, we're talking about that one. So if we know this, what I would do next is multiply both sides by Q. So then Q root 2 is equal to P. And I can square both sides, meaning that I get 2Q squared is equal to P squared. So now we know that P squared is an even number. Hopefully you'd agree with that. So then we can say that since Q squared is an integer by closure. Now, if P squared is an even number, what that means is then P is an even number. Those two imply each other. And so P is equal to 2x for some x in the integers. Now, so since P squared, though, is then equal to 4x squared, I'm using P squared here, drop down. These two are the same, since P is equal to 2x. Then 2Q squared, these two are equal. Divide both sides by 2, means that Q squared is equal to 2x squared. Using similar logic, I'm not writing everything all the way out. Please feel free to see it fully written out without speaking in the PDF. This implies that q squared is even, which implies that q is even. Oh no, this is where we get our logical inconsistency, and this is the symbol, this arrow, shows contradiction right here. So when you find your contradiction, mark it with that arrow. The contradiction here is we have said that P and Q are both even. However, P and Q are relatively prime. So what this has shown is that they have a common factor of 2. So 2 divides P and Q. Now, here's where contradiction comes in. Since we have arrived at something that is known to be false, and there's no false work here, that's where contradiction is definitely tricky. You have to make sure that it's not just you have made some error in your mathematics. This is an actual contradiction. Since P and Q must be relatively prime, by definition that 2 is a rational number, therefore the root 2 is not rational, and therefore root 2 is irrational. Now, contradiction can definitely get a little bit tricky for a lot of students. Because of this fact, you're always looking for something to go wrong, which is not necessarily something that we're used to. So let's look at another example. And I want to show you, the nice one about this is that it's going to be a helpful combination of both contradiction and contrapositive. So here it says, suppose that a is an integer. If a squared is even, then a is even. So the first thing I'm going to do is, since my conclusion is simpler, I'm going to start with the contrapositive, which would say that if a is odd, then a squared is also odd. And while we could prove this with direct proof, I do want to do a contradiction just as an example. You will get to the point next week for sure where you're going to have to choose between these 3 different options, but I want to show you how you can use contradiction in other cases. So here, if we're going to start with contradiction, that means that we must assume that this is false, meaning we do start with the hypothesis. So we're going to say a is odd, but a squared is even. So this is our contradiction statement. So we can start with the original. A is equal to 2x plus 1, since a is odd, where x is an integer. Since we're worried about a squared, I would write that out here in expanded form of 4x squared plus 4x plus 1. And this is going about it the same way that you would for any other type of proof. Very similarly, you'd say, all right, well then that would maybe be 2 times 2x squared plus 2x plus 1. Since 2x squared plus 2x would equal an element in the integers because it's closed under multiplication and addition, we now know that a squared is equal to 2y plus 1. So what we now know is that, okay, well, a squared is odd. Here's the contradiction, but we said a squared is even. They both can't be true. So therefore, the one that is assumed is the one that's untrue. So while it looks very similar to what we've done, we can still use contradiction just to arrive at something that is inherently false. So therefore, if a is odd, then a squared is odd. So again, we're working from 2 different ways, 2 different strategies, but most of the steps are exactly the same. So then by proof of the contrapositive, a squared is even implies that a is even. Hopefully this helped illustrate a very classic contradiction proof, and then one that is more well suited to a direct, but you can still see practice of both types, which I think is helpful. Please, as always, sign up for Zoom calls and things like that if you're stuck on anything, including the presentation, and I look forward to hearing from all of you soon. Talk to you later.